Hi, my name is Koen Verhagen. I'm with Sofics. In this short video presentation, I will talk about FinFET and FDSOI ESD Design Window limitations. FinFET and FDSOI technology basically provides us MOSFETs with less power consumption and superior performance. Due to the gate architecture, we can have significant enhanced drive strength. Further, due to the lower operating voltages, up to 50% of dynamic power savings can be obtained. The trend of declining operating voltages is shown on the left-hand side. If we follow the blue curve, we can see that for declining technology node feature size, the voltages are indeed dropping. That's the blue line. The red line is depicting the trend of the ESD robustness or transient voltage robustness of a gate oxide in these technologies. We can also see a fastly declining curve. The distance between the blue and the red line we can call the ESD design window, because obviously an ESD protection device shall operate below the area or region where damage may occur, so that's below the red curve. Also, the ESD device should not interfere with normal operation, so hence it should operate above the blue line. Hence, the distance between the blue and the red line can be called the ESD design window. It's the operational margin for the ESD protection device. If we go to the most advanced nodes, and for instance we focus on 0.8 volt FDSOI or FinFET technology domains, core domains, we see that merely 3 volts is left of the ESD design window. That is rather small. Further making this worse is the trend of the metal thickness as technology nodes are declining. ESD current will also be carried through metals on the chip, and hence the resistance of those metals is very important because it adds to the consumption of the ESD design window. As we can see on the right hand side, with technology nodes declining, we see thinner metals, and since that is inversely proportional to the resistance, we will see higher resistance. So let's have a look at the most traditional ESD approach, well known and common in use in the industry. It is the dual diode approach. It's called that way because we're using two diodes, one diode from the signal path up to the supply line and one diode down to the typically ground supply line. An ESD stress, or the general approach of this dual diode, is to divert ESD stress from the signal path to the power lines and then handle it locally by, depending on the polarity, the power clamp or a diode in parallel to that power clamp. Let's have a look at the case indicated by the yellow arrow. It is a positive stress on the signal path versus the ground line. In this particular case, the intended operation is to divert the stress through the diode up, flowing through the power line, which has some resistance, handled by the power clamp, and then again flowing through the bus resistance of the ground line. So the total voltage drop, or the consumption over the ESD design window in this case, is the drop across the diode, the drop across 2 times the resistance both in the power and the ground line, and also the voltage drop in the power clamp. So it's basically, as written by this very simplified formula here, the sum of the holding voltages in the diode and the power clamp and the resistive drop of the ESD current in the diode, the power clamp, and the bus resistances. That sum of voltages is actually presented to the protected node. In this particular case here, it is depicted as a gate, but it could be any circuit that needs to be protected. But the sum of those voltages is actually presented to that node. It leads to, in general, for the advanced technologies, that no core gates can be used in the I/O, and also no unstacked I/O gates can be used there because the sum of the voltages is adding up quickly. So how do we improve that? Well, the solution to that is called local clamping. Local clamping will use bidirectional clamps between the signal path and the ground and the signal path and the supply. As such, it decouples the ESD stress or the flow of the ESD stress from the power clamp, which may be distant and which also will introduce a voltage drop across power line resistance, both in the positive supply and the negative supply. Obviously, to implement this approach, we need very small and very efficient local clamps, where the PDK will suggest the use of cascoded clamps. We will see that if we want to use that the area consumption is rather large, and the design space use is also very important because of the sum of the holding voltages of cascoded devices. The Sofics solutions that are offered also and highlighted in this presentation for 2 kV are very, very small in the area. Some numbers are shown here for 5 nanometer technology and 22 nanometer technology. Obviously, more information can be obtained from Sofics. Here's the benchmarking of the Sofics solutions versus the traditional or PDK solution. The green curve is the traditional solution, the blue curve is the Sofics IP. You can see that the traditional solution is definitely effective, as we would expect, for the I/O gates, because it operates and conducts a nice amount of current, in this particular case more than 1 amp, below the limit where the I/O voltage gate would be damaged. However, you can also see that it's totally ineffective if core gates would be used, because its operation is way beyond the core gate limit. Hence the definition of the PDK limitations, saying that no core gates can be used in the I/O, and there also can be no gate connected directly between pad and supply, hence the no non-stacked use. The Sofics solutions, as you can see over here, are effective both for I/O gates and core gates, because the blue curve is operating well below the 2 orange lines. In this particular case, we also see a higher performance for more or less the same area design. Furthermore, having the ability to use core gates in the I/O will enable higher speed I/O designs and allows special features. So, thank you very much for listening to this short presentation. If you want to contact Sofics for more on robust solutions for ICs, please do so through the web at www.sofics.com or connect with us via email at bd@sofics.com. Thank you very much and have a very nice day.